Hello everyone, and welcome to Amazing Physics. Today, we're going to be talking about von Neumann architecture and Harvard architecture. Computer architecture is the study of the design and implementation of computer systems. It's a broad field, but we'll focus on the most important aspects of it. In this video, we'll talk about the two main types of computer architecture, von Neumann architecture and Harvard architecture. We'll discuss the key differences between the two architectures, and we'll see how they impact the performance of computer systems. By the end of this video, you'll have a good understanding of von Neumann architecture and Harvard architecture, and you'll be able to choose the right architecture for your needs. So, let's get started. First and foremost, what exactly is computer architecture? Well, computer architecture refers to a set of rules or specifications that dictate how computer software and hardware are combined and interact to create a functional computing platform. It's like the blueprint that outlines how all the different components of a computer system work together harmoniously. Think of computer architecture as the foundation upon which a computer is built. It not only defines how software and hardware interact, but also determines the capabilities and limitations of a computer system, from the type of processors it can support to the memory and storage technologies it can handle. Computer architecture plays a crucial role in shaping the overall capabilities of a computer. At its core, computer architecture is all about the interaction between software and hardware. It specifies how the software, such as operating systems and applications, can effectively utilize the hardware resources available. By defining the structure and organization of the system, computer architecture ensures that software programs can run efficiently and take full advantage of the underlying hardware. Additionally, computer architecture also determines which technologies a computer system is capable of handling. This includes the types of processors, memory modules, storage devices, and other components that can be integrated into the system. Different architectures support different technologies, and advancements in computer architecture often lead to breakthroughs in performance and capabilities. The computer architecture can be categorized into three main categories. The first category of computer architecture is system design. This aspect focuses on the hardware components that make up the actual computer system. It includes multiprocessors, memory controllers, CPUs, data processors, and direct memory access. The system design is responsible for orchestrating these hardware parts to create a cohesive and functional computer system. First up, we have multiprocessors. Multiprocessors are CPUs that can work together on the same task. By harnessing the power of multiple processors, the computer's performance can be significantly enhanced, often by a factor equal to the number of CPUs employed. Next, we have memory controllers. Memory controllers play a crucial role in managing the memory within the computer system. Their primary function is to ensure that the CPU has timely access to the required memory resources whenever it needs them. This coordination helps optimize the overall performance of the system. The CPU, or Central Processing Unit, is the heart of the computer system. It acts as the brain, carrying out the instructions that drive the computer's operations. It performs calculations, executes tasks, and coordinates the flow of data within the system. Without a CPU, a computer would be unable to function. Data processors are responsible for processing data within the computer system. They can perform various tasks, including encryption, compression, and data mining. Data processors enable the manipulation and transformation of data to meet the needs of different applications and functions. Lastly, we have direct memory access, commonly known as DMA. DMA is a technique that allows devices to access memory directly, without involving the CPU. By bypassing the CPU, DMA can significantly improve system performance by reducing the CPU's involvement in managing memory operations. Moving on to the second category of computer architecture, we have instruction set architecture, or ISA. ISA revolves around the CPU and encompasses its capabilities and functions. It defines various aspects, including data types, processor register types, memory, input, output operations, and instructions that computer programmers utilize. The first component of an ISA is the set of instructions. These instructions are like commands that the processor can understand and execute. Each instruction has a unique opcode, which is a binary number that tells the processor what operation to perform. For example, there might be instructions for addition, subtraction, branching, and many more. Now, let's talk about the data types supported by an ISA. A processor can manipulate various types of data, such as integers, floating point numbers, and characters. The ISA defines how these data types are represented and processed within the processor. This ensures that the software and hardware agree on how to interpret and operate on different types of data. Another crucial aspect of an ISA is the set of registers. Registers are small, fast memory locations within the processor that can be directly accessed. They are used to store data that the processor needs to work with quickly. The ISA specifies the number of registers, their sizes, and the operations that can be performed on them. Moving on, let's discuss memory. Memory is where the processor stores both data and instructions. The ISA defines how the processor can access and manipulate data in memory. This includes operations like reading data from memory, writing data to memory, and transferring data between registers and memory. Lastly, an ISA also covers input, output, or I/O operations. These operations enable the processor to interact with peripherals such as keyboards, mice, printers, and more. The ISA specifies how the processor communicates with these devices, allowing it to send and receive data or control their behavior. Finally, we come to the third category of computer architecture, which is microarchitecture. Microarchitecture defines the physical implementation of an instruction set architecture on a physical processor. It's how the hardware of a processor is designed to execute instructions efficiently. It includes storage elements such as register file, arithmetic logic unit, control unit, pipeline, cache, and memory controller. Additionally, microarchitecture encompasses data paths, which are the interconnecting wires that facilitate the flow of data between different components of the CPU. The first essential component of microarchitecture is the register file. The register file is a small, fast memory within the processor that stores data and instructions temporarily. It enables the processor to quickly access and manipulate data, improving overall performance. Next, let's talk about the arithmetic logic unit. The ALU is the heart of the processor, responsible for performing arithmetic and logical operations on the data. It executes instructions such as addition, subtraction, bitwise operations, and comparisons. The control unit plays a vital role in microarchitecture. It coordinates and orchestrates the activities of various components within the processor. The control unit fetches instructions, decodes them, and directs the ALU, register file, and other parts of the processor to perform the required operations. To enhance performance, modern processors often employ a technique called pipelining. The pipeline allows the overlapping execution of instructions. It breaks down the instruction execution process into multiple stages, enabling the processor to process multiple instructions simultaneously. Cache is another crucial component of microarchitecture. It is a small, fast memory that stores recently accessed data, reducing the need to fetch data from slower main memory. Caches help improve performance by minimizing memory access latency. Lastly, we have the memory controller. The memory controller manages the flow of data between the processor and memory. It ensures efficient data transfers, handles memory requests, and optimizes memory access patterns to minimize delays. And there you have it, the three main categories of computer architecture: system design, instruction set architecture, and microarchitecture. Each category plays a crucial role in shaping the overall functionality and performance of a computer system. By understanding these aspects, we gain insights into how hardware and software work together to create powerful computing platforms. Now that we have explored the three main categories of computer architecture, let's shift our focus to two specific types that have significantly shaped the field: von Neumann architecture and Harvard architecture. What is von Neumann architecture? Von Neumann architecture, named after the brilliant mathematician John von Neumann, is a computer architecture model that revolutionized the way computers are designed and operated. It was first proposed by von Neumann in 1945 and remains the foundation of most modern computers. Let's take a brief look at the history of von Neumann architecture. In 1945, John von Neumann, a prominent mathematician at the time, introduced the concept of a stored program computer. This concept was a significant departure from earlier computer generations that were hardwired to perform specific tasks. Von Neumann's breakthrough idea was that a computer could execute any task as long as the program was stored in memory. One of the primary advancements in von Neumann architecture was the concept of conditional control transfer. This allowed program sequences to be interrupted and resumed at any point, making programs more flexible and efficient. Another fundamental aspect is the use of a single memory unit to store both instructions and data. Unlike earlier systems with separate memory units, this integration simplified programming and improved overall efficiency. Now, let's explore the key components of von Neumann architecture. First, we have the arithmetic logic unit, responsible for performing arithmetic and logical operations on data. Next, the control unit governs the execution of instructions, coordinating the activities of other components. The memory unit stores both instructions and data, providing a unified storage space. Registers, small and fast memory units, store data being processed by the OLU. Input-output devices enable the computer to interact with the external world. So, how does von Neumann architecture work? Here are the basic steps. First, the control unit fetches an instruction from memory. Next, it decodes the instruction and determines the operation to be performed. Then, the control unit sends signals to the arithmetic logic unit to carry out the operation. The OLU performs the operation and stores the result in a register. The control unit fetches the next instruction and repeats the process. Like any architecture, von Neumann has its advantages and disadvantages. One of the key advantages of von Neumann architecture is the unified retrieval of instructions and data from the same memory unit. This simplifies the development and design of the control unit, streamlining the overall system. Additionally, this unified memory access allows both instructions and data to be accessed in a similar manner, increasing overall efficiency. Another advantageous characteristic is that programmers have control over memory organization. They can manage how data is stored and accessed, optimizing their programs for performance. However, like any architecture, von Neumann also has its share of disadvantages. Let's explore a few of them. Firstly, due to the serial processing of instructions, parallel executions of programs are not possible. This limitation can impact the overall speed and efficiency of the system, particularly in scenarios where parallel processing could be beneficial. Another disadvantage lies in the shared bus architecture. As only one bus can be accessed at a time, the CPU may be idle while waiting for data transfer, leading to potential performance bottlenecks. This is commonly referred to as the von Neumann bottleneck. While the integration of instructions and data in the same memory unit has its advantages, it can also result in data loss if errors occur in a program. Overwriting data mistakenly can lead to the loss of valuable information. Furthermore, if a defective program fails to release memory when it is no longer needed, it can cause the system to crash due to insufficient available memory. And there you have it, the fundamentals of von Neumann architecture, some of its advantages and disadvantages. It offers a simplified design, unified memory access, and programmer control over memory organization. However, limitations such as the lack of parallel execution, the potential for data loss, and the possibility of crashes due to memory mismanagement should also be considered. Now let's move on to Harvard architecture. So what is Harvard architecture? Harvard architecture, first proposed by Howard H. Aiken in 1943, stands as an alternative to the more commonly known von Neumann architecture. This model is based on the concept of storing instructions and data in separate memory units. Let's take a closer look. The Harvard architecture found its origins in the Harvard Mark I computer, constructed in 1944. This electromechanical marvel utilized separate memory for instructions and data, allowing for simultaneous fetching of both. This simultaneous access greatly enhanced the performance of the system. The main components of Harvard architecture include an arithmetic logic unit for performing operations, a control unit to oversee instruction execution, separate instruction and data memories, registers for temporary storage, and input-output devices for interaction with the outside world. Here's how Harvard architecture works. First, the control unit fetches an instruction from the instruction memory. Next, the control unit decodes the instruction and determines the operation to be performed. Then, the control unit signals the OLU to carry out the operation. The OLU performs the operation and stores the result in a register. Finally, the control unit retrieves the next instruction from the instruction memory, repeating the process. Harvard architecture offers several advantages over the more common von Neumann architecture. One significant advantage of Harvard architecture is the reduced chance of data corruption. With separate buses for instructions and data, the risk of unintended interference or corruption is minimized, ensuring the integrity of both components. Furthermore, this architecture allows for instructions and data to be accessed in the same way, simplifying memory access and enhancing efficiency. The simultaneous flow of data and instructions, facilitated by separate memories and buses, leads to high performance. This simultaneous access allows for efficient processing and faster execution of tasks. Additionally, Harvard architecture provides greater memory bandwidth, which is more predictable due to the separation of instruction and data memory. This can result in improved system performance and responsiveness. While Harvard architecture offers several advantages, it also presents a few challenges. One such challenge is the need for balanced memory allocation for instructions and data. The manufacturer must carefully allocate memory resources, ensuring optimal utilization for both components. Moreover, the implementation of Harvard architecture requires 2 buses, making the system more complex and time-consuming to manufacture. This complexity and additional hardware components contribute to increased system costs. The complexity of Harvard architecture also poses challenges for mainboard manufacturers, as they need to design and implement the system with careful consideration of the 2-bus structure. In conclusion, Harvard architecture provides advantages such as reduced data corruption risk, efficient memory access, high performance, and predictable memory bandwidth. However, it also brings challenges, including the need for balanced memory allocation, increased complexity, and higher manufacturing costs. Here is a table that summarizes the key differences between von Neumann architecture and Harvard architecture. Von Neumann architecture is the most common type of computer architecture. It is based on the stored program concept, which means that instructions and data are stored in the same memory. This architecture is simple and efficient, and it is used in most general-purpose computers. Harvard architecture is less common than von Neumann architecture. It is based on the Harvard Mark I relay-based computer model, which means that instructions and data are stored in separate memory. This architecture is more complex than von Neumann architecture, but it can be faster and more secure. Harvard architecture is used in some specialized applications, such as signal processing and microcontrollers. Thanks for tuning into our video. If you found this information helpful, remember to give it a thumbs up and subscribe to our channel for more exciting discussions. We're always here to answer your questions and engage in the comments section below. Don't forget to share this video with your friends so they can benefit from the content as well. Press the bell icon to receive notifications whenever we upload new videos. Stay tuned for more informative content coming your way.